Alright, welcome to week 9's workshop. We've got our integration continuing with the following, so we'll get on with it. Okay, so these are indefinite integrals, and we'll get on to some definite integrals a bit later on. Alright, so what we want to do is learn about the process. Sometimes when you get a story given to you in a particular system of curriculum, it's not always obvious what's going on. So this is actually referring to the idea that you can call this integration by substitution, but a form of this represents a quotient. And so I'm going to express it this way. So we express the quotient as the function with a quotient with its derivative above. Now, if it turns out that the function has a derivative on its numerator and the function's on the denominator, then we can simply substitute it with the function itself plus c. So it's just a straight out substitution. So if we have a look at this example here, and of course you'll often get them written this way in this particular type of textbook or what have you, but you can redo it yourself. So then what we look to do is to understand our quotient. We can't do up and under on this. Up and under it still requires us to interpret the quotient. This is my point. So it still requires us to understand that what we're saying here is the integral of 1 over x, and what that represents is what's the derivative of x is 1, so it's of this form. It's of this form. Because it's of this form, we can write it as the ln of x plus c. So that's a very simple one. This is also the same. Is the derivative of x plus 2 on the numerator? The derivative of x plus 2 is 1, so yes it is. So as it is of the form, integrating a derivative on the numerator and its function on the denominator, because it is of this form, we can substitute. So that's just a straight substitute. So the integral becomes the ln of x plus 2 plus capital C. Okay, very straightforward. So it doesn't matter if it's a more absorptive. I would be encouraging you to do this way rather than using the substitution, integrations substitution. Alright, so let's have a look at another example where we have the derivative. So this one here, we'll write it just as a bit of pre-work, just because we can. 3x minus 1 dx. Now, is the derivative of the numerator, is the derivative of the denominator on the numerator? And of course the answer is no. So we have to come up with a solution. And we rely on the idea of the 1 times table. 1 multiplied by anything. Now watch this. Really? You can multiply it by a whole. Wow. It will not change it. Now, it might not look the same, and I'll show you that, but it is no change, okay? And keeping in mind also, when we use this technique, we often have a constant, and often it's the constant that's brought out, f of x dx, okay? So that constant's often brought out the front, okay, as it is here. So let's think about the form of 1. What's the form of 1? Well, it's a quotient. So let's see, is it the form of 1 over 1? The f dash of over x? No, it's not. Because the derivative of 3x minus 1 is 3, and 3 is not on the top. So we need to introduce a form of 1 where we multiply by this integral such that it doesn't change it. Now, we've done this quite a lot in other areas. So the form of 1 that we're going to use is 3 over 3. It's the integral of 1 over... Now, I'm doing every step here just so that you get familiar with this. And so what this will be is 1/3 times 3 over 1 integral of 1, 3x minus 1 dx. Now look what I can do here. I can invoke this rule, and I can take that 3 and place it over that sign. So we get 1/3 the integral 3 over 3x minus 1. Now, is this of the form f dash of x over f of x? And the answer is yes. So we can then substitute. This allows us to write 1/3 the ln of the denominator plus capital C. Now you're going to use this quite a lot in your travels as you go forward into Maths 1. So it's very important that you learn to cope with this whole idea of a 1 multiplier. Okay, so let's have a look at this one. The derivative, it's a quotient. Up and under is not going to be very helpful. So it's a quotient. What's the derivative of the denominator? 5. Is that on the top? No, it's not. So we're going to move the 3 over. So we'll have 3, the integral 1 over 5x plus 2. Why do we do that? Because we can. It's our convenience. The next thing we'll consider is that we're going to have a 1. What's the 1 we need? 5 over 5. Okay, what are we going to do with that 5? We're going to put it over. We're going to put it over, and so it will become 3/5 integral 5 over 5x plus 2 dx. So therefore, we now have our integration. Now look at all the steps we've done, and we still haven't done any integration whatsoever. So let's go ahead and do that. So it is of the form f dash of x. So now we can write 3/5 the ln of the denominator. Wow. We will use this a lot in advanced maths, in extension maths, 1 or 2 in maths 2. Alright, so we can do this through the lens of 1 over x. And I'm going to do that now, but really what I prefer you did is what I sought to do here. Okay, so let's think about doing a u substitution. If we let u equal ax plus b, then du dx is simply a, and if we just do the cross multiplications, 180u is equal to dx. So this is the thing we come to change here. So we've got 1 over ax plus b dx. Are you up there? Yeah, there I am. So you're now being substituted out for du, and 1 over a, that's the convention, and this thing's wing, so it's 1 over u. Now 1 over u, as we've already seen in the opening part, is in fact the derivative of its function over u. So we can just simply say, alright, that's the form of f dash of x over f of x. Yes? So we can write 1 over a equals the ln of u plus c, and so that is 1 over a the ln of ax plus b. So very straightforward, just recognising the use of this 1 over u. Alright, so let's have a look at some more examples. Here's an example here. We've got another one. The derivative of this quotient is 2x. Is 2x on the top? Not quite. So what we need to do is we need to multiply this particular derivative by 1 and thus not change it. What's the form of 1? Well, we need to borrow a 2. X squared plus 7. And but 2 will go over, it's next to there because we're allowed to do that by the constant rule, and so it will become a half the integral 2x over x squared plus 7. Now, is the derivative of the denominator on the numerator? Yes. Okay, yippee. So we're going to go straight to a substitution where we have a half of ln of x squared plus 7 plus capital C. And that's our final point. So we're just using that same idea over and over again, but once you get the hang of them, they're fairly straightforward. Alright, is the derivative of differential sine is cos. Whoops. So it's already of that form. So we can go straight to a substitution. Sine x plus c. Wow. That's amazing. Alright, so sine x plus c. Very good. Alright, so for our next one, this one's going to require us to do a bit of thinking. Okay, a little bit of thinking because we're not used to dealing with the chain rule to the extent that we are expected to do in Maths 1. But that's alright, we're getting closer and closer each week as we go. By the time we get to Maths 1, we'll be right. So if I'm going to rewrite this just to be a little pedantic, e to the 2x over 1 plus e to the 2x dx. Okay, so what is it about this? There's just a little bit of noise there interfering with that. So e to x over 1 and then the x goes out the back. Now, we've got a little problem here because we're asking, is it of the form the derivative over the function? Is it of that form? And the answer is we're not sure because we have to do 1 plus e to the x. Okay? In other words, we have to discover if 1 plus e to the 2x is, so let's do that. Okay, du dx. Well, I think that it turns out that if we do the chain rule, we have to ddx this one. One will clearly disappear, but e to the 2x requires a chain rule. So we're going to let m equal to x, and then we've got to change this to ddm, and so that'll be em, and this one over here will be dm dx. Now that's 2x, so that'll be 2, and this is e to the m. So we get, as a chain, 2e to x, 2e to the 2x, so du dx. So what we can see is that do we have e to the 2x? Well, we do. 2e to the 2x. So rearranging this, you get 1/2 du is equal to e to the 2x dx. So we can just ask ourselves, do we have u? Yep. Do we have u? Yep, there you are up there. So it's also gone. So those two things are being substituted out for a half u. So we can write out the u here. It substitutes out those and a half. So we get the integral 1 over u. Now u is itself 1 plus e to the 2x. So this becomes derivative. Is the derivative of u 1? Yes, it is. So we get a final integration of 1/2 ln of u, which we'll put back in now as 1 plus e to the 2x plus c. That should be a capital C.